Welcome to Study Loop.
Hi everybody, thanks for joining us today. So what we have here is a problem that is using the conservation of energy, and what we're given is that a car starts from point A, from rest, coasts down to point B, and then from point B onwards the brakes are applied to where the car is brought to rest at point C. So what we're asked to find is what is the velocity at point B and the coefficient of friction between the ground and the car's tires from B to C. So what we're given also is the mass of the car, 2,000 kilograms. The theta, the angle of this ramp, is 6 degrees. We know that the car is starting from rest at point A. And then we also have some information on the distances from A to B, which is 150. We're going to call that H1. And then the distance from B to C, we're going to call that H2, and that's 20. So the first thing that we're actually going to do is just draw a simple free body diagram to identify the forces that are acting upon this car. So at point A, we see that this car is on a ramp with an angle theta, and as with anything with mass, there's a weight force, and since this car is on a ramp, there's also a normal force acting on the car from the ramp. Now we're going to move on, and to actually solve for the velocity of B, we're going to use the conservation of energy. So we know that the energy at point A, total energy, is equal to the total energy at point B, since there's no friction involved. Since we know that the car is starting from rest at point A, the only energy at point A is actually the potential energy. And this potential energy is given by the mass times gravity times the height at which this car is at. Now if we go back to the original figure, we can see that if we choose R0 to be point B, the height that the car is at is this distance right here. And that is actually going to be equal to H1 times sine theta. That's just basic trigonometry. So we're going to say H1 sine theta. And since we chose our 0 to be at point B, there's no potential energy at point B. So therefore, the only energy at point B is actually kinetic energy, which I'm just going to call KEB, and that's what we don't know. That's 1/2 mvb squared. So if we set these equations equal to each other, we know that PA equals KEB, which is equal to mgh1 sine theta equal to 1/2 mvb squared. Now we see that the masses cancel out, and if we solve for VB, we can see that VB is equal to 2gh1 sine theta, and the square root of that is equal to VB. Now once we plug in the values that we know, we actually know all these values. G is just 9.81 meters per second squared, H1 is 150, and theta 6 degrees. We get a VB of 17.54 meters per second, and that is the first part of our answer. Now remember, we also have to solve for mu, and that is the coefficient of friction between the car's tires and the ground. Now we're actually going to use a similar equation that we use. We're going to use this conservation of energy again, and what we're going to do is we're going to say that the energy at B is equal to the energy at C. However, we must remember that friction is involved, which is a non-conservative force. So there's work done by it that isn't recovered. So we have to add the energy from friction, which I'm just going to designate as F. We'll make that EF just for energy. So if we set our, we're going to have to choose another 0 again this time. And this time I'm going to set my 0, remember this is point C, this is point B. I'm going to set my 0 at point C just to make things a little easier. So remember now, EB, the point energy at point B, is going to be the potential energy plus the kinetic energy that we know. That's equal to EB. Remember that EC is equal to 0 because potential energy is 0. As well, let me make that potential energy at C is 0, as well as the kinetic energy is 0, because remember, the car is brought to rest by those brakes. So what we actually have is just an equation that is EB is equal to the energy that is lost by friction. So, continuing forward, we see that PB will be equal to, remember that this is H2 that we had from before, PB is going to be equal to mg H2 sine theta. Kinetic energy at B will be 1/2 mvb squared. And now we have to define our EF, which is the energy lost to friction. So now let's remember that the formula for friction is mu times the normal force. And then since this is work done, we also have to multiply by the distance that the work is done over, which is going to be H2. So knowing these, we see, what do we know? We know H2, but what is N? So now this is where that free body diagram that we made a long time ago comes in handy, right? So if we scroll up, back to the free body diagram, this is N, and we see that the normal force will actually be equal to a component of the weight force. So if we were to break these forces down into their components, I'm breaking the weight force down. This is the weight force broken down into those components in the direction of acceleration. I want to also draw the triangle that represents the position of theta. We see that the normal force is actually equal and opposite to the weight cosine theta, because the normal force is actually acting directly opposite of that. So this is our normal force. So now if we scroll back down, we can write this in, and we can say that EF is equal to mu mg cosine theta times H2. So let's set everything equal to each other. So we know that EB is equal to mgh2 sine theta plus 1/2 mvb squared, and that's equal to EF. Right, so what this gives us is mgh2 sine theta plus 1/2 mvb squared is equal to mu mg cosine theta H2. So now what we have is an equation that where we can cancel all the m's out, as you can see, and we solving for mu, this gives us gh2 sine theta plus vb squared over 2 all over h2g cosine theta, which gives us mu, and plugging in the values for all these quantities that we have here on the left, we find that mu equals 0.893. Thank you.